Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 9, Lesson number 2 on irrational numbers. Before we begin, let me just remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes at the top of every worksheet. Scan those codes with your smartphone or with your tablet, and they'll bring you right to the video that's associated with that lesson. All right, let's begin. Numbers are an amazingly fascinating thing. You know, we, in a certain sense, almost invent numbers to satisfy purposes that we have. All the numbers that you deal with are known as real numbers. Eventually, in Algebra 2, you'll also learn about what are known as imaginary numbers and complex numbers. All right, but for now, we're just dealing with the real number system. And real numbers are broken down into two distinct categories. And by distinct, I mean they don't overlap, okay? And those two categories are rational numbers. Rational numbers are numbers that can be written as the ratio of two integers. Numbers like 3/4, which is the ratio of 3 to 4. Or -7/3, which is the ratio of -7 to 3, or 7 to -3, and something like the number 5, which can be thought of as the ratio of 5 to 1. Those are all ratios of two integers. Rational numbers have terminating or repeating decimals. For example, 3/4 is 0.75. That's a decimal that just terminates. -7/3 is -2.33333333, right? It repeats. And of course 5 is, well, if you will, 5.0. You can think about that as terminating or repeating, 5.00000. All right? Irrational numbers, on the other hand, are simply any numbers that aren't rational. That's all they are, right? So you got the rational numbers, and then you have the irrational numbers, right? And of course, what that means is that if an irrational number is not rational, then they must have non-terminating and non-repeating decimals. In other words, their decimals go on forever without any repeating pattern. Okay? So we're going to be working with irrational numbers today, and it's a very complex topic. I actually question whether it's appropriate at this level, but it's something that you're supposed to understand a little bit of at the Common Core level, okay, Common Core Algebra 1 level. So let's move in and start to take a look at them a little bit. Okay, exercise 1 says, let's consider a number that's rational and a number that is irrational. Consider the rational number 2/3, which is obviously the ratio of 2 to 3, and the irrational number, the square root of 1/2. Now you just have to trust me right now that the square root of 1/2 is irrational. Both of these numbers are less than 1. All right, letter A says draw a pictorial representation of 2/3 of the rectangle shown below. So the whole point of rational numbers, right, the ratio of integers, especially positive ones, is that you could take a whole, all right, and you could break it into a certain number of parts, equal parts, 3 equal parts, right? Those are supposed to be equal. And then this tells me how many of those two parts I should take. Let me do it in red, right? That's what a rational number is. So this is a pictorial representation of the number 2/3. I take a whole, I break it into 3 parts, and I take 2 parts of it. The reason that, of course, rational numbers were invented by human beings was because we can't always measure things in whole numbers, right? Sometimes we want just a fraction of them, okay? Now, letter B says, use your calculator to give a decimal representation of the number 2/3. Notice that it has a repeating decimal pattern. So what I'd like you to do real quickly is pause the video and type in 2 divided by 3 and see what it tells you. Now, you might see on your calculator something that looks like this. And again, I'm not going to actually bring open the TI-84 Plus right now, but you might say, whoa, look at that, that's a 7. Something's wrong here. Well, there isn't anything wrong. What the calculator has done is it's showed you every decimal it can fit on the screen, and then it rounded the last decimal because there's more sixes. They just keep going on forever. In fact, what we would say is we'd say that 2/3 is 0.6 repeated, right? Now, letter C, let's take a look at what the decimal representation of an irrational number looks like. Okay, so pause the video really quickly and please type in the square root of 1/2. All right, now depending on your calculator, how new the TI is that you're using or whatever calculator you might have, it may look like this, it may look like this, and trust me, there's no way for me to remember all the decimals here. That's one of the tricky things about an irrational number. So I have to kind of look over at my cheat sheet. Sorry about that, but I don't really want to open up the TI-84 at this point. And look at this, right? Now, you might say, well, but it terminates. Well, it doesn't terminate. Again, your calculator is showing you every decimal that will fit on the screen, and the problem is it goes on forever. So there is no repeating pattern here, right? No repeating pattern. Now, letter D. Why could you not draw a pictorial representation of the square root of 1/2 the way you do for 2/3, right? So we could never draw something like this for the square root of 1/2. Why is that? All right, well, this is actually quite tricky in my mind. Because the square root of 1/2 is irrational, it cannot be written as the ratio of two integers. And because of that, thus, we cannot divide the whole up into an integer number of parts, right? So for 2/3, literally what 2/3 tells us is that we take a whole, we divide it up into 3 smaller parts, and we take 2 of them. But if we can't write a number like the square root of 1/2 as a ratio of integers, then there's no way to ever take the whole and divide it into those 3 parts or 7 parts or whatever. See, if we knew that the square root of 1/2, and it's not, but let's say we knew that this was 7/10. It's not, okay, I really want to emphasize that. Well, then we would just take our whole, divide it into 10 parts, and take 7 of them. And that would be the square root of 1/2. But we can't do that because it's an irrational number. So therefore, there is no way to pictorially represent it in terms of dividing a whole into a certain number of integer parts and then taking that number of parts. That's pretty deep, pretty deep. Irrational numbers are super cool at the deep level. They're a little bit annoying at the sort of superficial level that we're attacking them at, because what do we really know about them? Well, you can't write them as the ratio of two integers, by definition, right? And they have non-repeating, non-terminating decimals. Yay! Okay. Anyway, let's play around with them some more. All right? I'm going to clear out this text, so write down anything you need to. All right, here we go. Let's move on to the next page. Common irrational numbers. Well, you've seen one. You know, you haven't seen it for many years, but you've seen it. And it's probably the most important irrational number of all, and that's the number pi, right? The number pi is intimately related to circles. In fact, where you've probably seen it the most often is calculating the circumference of a circle, the distance around a circle, right? The circumference of a circle is always pi times the diameter of a circle, right? Where pi is like 3.1415, etc. I mean, it's irrational, so it never terminates. Now, you won't really play around with pi very much in this course. Wait until geometry, then you'll see it quite a bit. But the ones that you're going to see in this course are square roots of non-perfect squares. And you're going to have to trust me on this. The proof of the fact that the square root of a non-perfect square is irrational is really kind of cool. but it's beyond the scope of this course. But numbers like the square root of 15. 15 is not a perfect square, so that's an irrational number. The square root of 6 is an irrational number. The square root of 17, an irrational number. See, 15, 6, 17, 40, none of those numbers are perfect squares, so all of their square roots are irrational numbers. Now, beware, square roots of perfect squares are rational numbers, right? The square root of 25 is 5, and 5 is a rational number. It's the ratio of 5 to 1, okay? So what you don't want to think is that anytime there's a square root, you have an irrational number. You know, here's one involving a fraction. The square root of 1/9. Sorry, the negative square root of 1/9 is negative 1/3. Perfectly good. It's the ratio of negative 1 to 3, or 1 to negative 3. All right. So we're going to work with these quite a bit today. Let's keep moving. Okay, so just a little playing around. I want you to see what irrational numbers look like in their decimal form. So in this case, we've got the square root of 2, the square root of 10, and the square root of 23. 2, 10, and 23 are all non-perfect squares, and therefore their square roots are irrational. What I'd like you to do is pause the video right now, use your calculator to find the square root of each of these numbers, and write out every decimal it shows you, okay? Take a moment to do that. All right, let's go through them. And again, you'll have to excuse me for kind of looking over to the side because I can't do these in my head. In fact, it would be very difficult to do them in your head. The square root of 2, which is a very important number, is 1.41, whoops, and then I botched it immediately. That was wonderful. 1.414213,562. And you have to write it in this wavy way. Not really. But notice there is no repetition there, right? We don't see a pattern that picks up and then repeats itself. The square root of 10 is 3.16227766. Now that's a cool looking pattern, but it's not a repeating pattern. If we had seen something like this, 162, 162, 162, that would indicate a rational number. But that's not what we see. So don't be fooled by the 22, 77, 66. That's irrelevant. The square root of 23, 4.7958311523. Again, absolutely nothing there that we see repeating in terms of a pattern. All right. And this is important because, many times if you're thinking about whether a number is rational or irrational, it could be helpful to just take out your calculator, throw the number in there, and see what kind of decimal pattern it has. Okay? Anyhow, I'm going to clear this out. There's nothing too special about it. And then we're moving on. Okay, here we go. Next problem. So, let's play around with an irrational number. Okay, it says, exercise 3, consider the irrational number square root of 28. Well, since 28 is not a perfect square, we know that the square root of 28 is irrational, or at least I know it is, and I told you it was, so hopefully you trust me. Now letter A is kind of cool. Without using your calculator, between what two consecutive integers, right, there's that consecutive integer piece, will this number lie, and why? All right, pause the video and think about the two consecutive integers. So does it lie between 10 and 11? Does it lie between 1 and 2? What does it lie between? All right, let's take a look. Well, here's how we do it. Hopefully this will make sense. The square root of 28 must lie between the square root of 25 and the square root of 36. If we wanted to get fancy, we could use inequalities. So the square root of 28 is greater than the square root of 25, and the square root of 28 is less than the square root of 36. But that means the square root of 28 must be greater than 5 and must be less than 6. So it lies between 5 and 6. Another good way of thinking about it is that 5 squared is 25, 6 squared is 36. So since 28 lies between that, the square root of 28 lies between 5 and 6. Simple enough. Now letter B says, using your calculator, write out all decimals for the square root of 28. So go ahead and do that really quick. Pause your video. Okay, well, let's take a look. All the decimals, again, I have to do a little cheating here. 5.291502.622. All right, so nothing repeating, right? We just want to see that non-repeating pattern. Now, letter C, write the square root of 28 in simplest radical form, right? This is what we did in the last lesson, quite a bit in the last lesson. Now remember, what we're doing in that case is we're looking for the biggest perfect square, right? Let me just write out some of them. We're looking for the biggest one of these that goes into 28 nicely. So which one is a nice divisor of 28? And that happens to be 4. So let's say that we take the square root of 28 and we make it into the square root of 4 times 7, which means it's the square root of 4 times the square root of 7, which means it's 2 radical 7. All right? Now what I'd like you to do is take your calculator and write out the decimal representation for 2 times the square root of 7. So literally, pause the video and just write in 2 times the square root of 7. Enter, and see what you get. All right, well, hopefully you got exactly what we got last time. And you have to, because when we simplify a square root, we are coming up with an equivalent expression, right? We're coming up with exactly what we had before. It just is, for some reason, considered simpler. Now, we could debate whether 2 root 7 is simpler than root 28, but that's just the name we're giving to it. Now, think about this for a second. This is kind of cool. This is a rational number, right? 2 is a rational number. And the square root of 7, I don't want to claim 7, but the square root of 7 is an irrational number. But that means a rational times an irrational must be an irrational. Unless, of course, we had 0. If I had 0 times, let's say, the square root of 10, that would be 0. And that 0 is a rational number. So besides 0, a rational number times an irrational number will be irrational. All right? We're going to summarize this in just a moment. So write down what you need to. Pause the video. Okay, here it goes. So, in summary, the product of a non-zero rational number and an irrational number results in an irrational number. So if I asked you, is this number irrational or rational, you'd say, well, that's irrational, that's rational, and therefore the product must be irrational. All right? So the product of a non-zero, I hate the fact that we have to throw that in there, don't you? It'd be great if I could just say, hey, the product of a rational number and an irrational number is irrational. The problem is 0 is a rational number, and 0 times anything is 0. That's the zero product law, right? So it's good to know this. All right, I'm going to clear out the text, and let's play around with this some more. Whoops, wait, I got to go back to that question for a second, right? But what about the sum of a rational and an irrational number? The product is irrational, but maybe when we add a rational to an irrational, maybe then it turns out to be rational, all right? So let's play around with that a little bit in the next exercise. Okay, exercise 4 says, for each of the following addition and subtraction problems, a rational number has been added to an irrational number. Write out the decimal representation that your calculator gives you and classify the result as rational if it has a repeating decimal or irrational if it doesn't. All right. Now this is pure calculator work and some work with like looking at the decimals. So why don't you go ahead and do that? All right. Actually, let's do the first one together. Okay. So literally, if I take my calculator out, and I'm not going to open up the TI-84 Plus to do this, but if I type in 1/2 plus square root of 2, and then I hit enter, this is what my calculator gives me. 1.91421 1, 3, 5, 6, 2. Now, I don't know about you, but I don't see any repeating decimal representation there. So I'm going to say this is irrational. All right. What I'd like you to do is do the same thing in letter B and letter C. All right, let's go through it. So again, if I type in the rational number 4/3 plus the irrational number square root of 10, my calculator gives me the following. 4.495610994. So I don't see any repeating decimals there. Therefore, we're going irrational again. And finally, if I ask my calculator to do 7 minus the square root of 8, right, a rational number minus an irrational number, right, we could think about that as plus negative 8, then I find 4.171572,875. I hope I'm writing all these down correctly. I'm looking at some pretty small type on my paper right now. But again, I don't see anything repeating, so again, irrational. And this is not a coincidence. In fact, we can state this as a general principle. When a rational number is added to an irrational number, the result is always irrational. All right? Which is kind of cool. It sort of makes sense to me from that decimal idea. You know, especially if I took a terminating decimal and I added it to one that was non-repeating and non-terminating, to me it makes sense that it would be non-repeating and non-terminating, okay? So when I add a rational number to an irrational number, the result is always irrational. Believe it or not, that is an actual Common Core standard. You're supposed to know that fact, all right? How important that fact is questionable, especially compared to all of the other very important work you've done in this course. But it is something that you're expected to know. Rational plus irrational gives you irrational. All right. Well, let's clear this out. Write down anything you need to and pause the video. All right. Let's do one more problem. Nice multiple choice question. Which of the following is an irrational number? Irrational, not rational. If necessary, play around with your calculator to see if the decimal representation does not repeat. Don't be fooled by the square roots. All right? So pause the video now, think about this problem, and if you absolutely need to, use your calculator, okay? All right, well, let's talk about it. See, the reason that I put in, not that this would show up on a standardized exam, but the reason I put in don't be fooled by the square roots is that a lot of students will learn, oh, the square root of a number, oh, that's irrational. Well, but number one, the square root of 25 is 5. That's a rational number. You know? Then some students will really be good about studying and they'll learn that, oh, when you add a number without a square root to a number with a square root, it's irrational. Well, not number 2, right? Square root of 9 is 3, so that thing's just equal to 1, and that's also a rational number. Now, by its very definition, number 3 is rational because it's the ratio of two integers, 7 to 2. So that's rational, which really just leaves me choice 4. But that's definitely irrational because we have a rational number. 6 is a non-perfect square plus an irrational, and that gives me an irrational number. All right? You can do that by typing each one of these 4 into your calculator, and what you'd see is that the only one that would even have sort of like a non-terminating decimal would be number 4. All the other 3 would actually terminate. You'd have 5.0, 1.0, and 3.5. The fourth one, though, would be non-terminating and non-repeating. All right, well, I'm going to clear out this text, so pause the video now if you need to. All right, here it goes. Let's wrap. Okay, so today You probably saw your second, maybe even third exposure to irrational numbers, numbers that cannot be written as the ratio of two integers. We saw that rational numbers had terminating or repeating decimals, whereas irrational numbers had non-terminating, non-repeating decimals. We also learned that when you found the product of a rational number with an irrational number, you almost always got an irrational number, unless of course part of the product was zero. And we found that you always will get an irrational number when you add a rational to an irrational. The most common form of an irrational number you'll see in this course will be the square root of a non-perfect square. All right, so we'll see this topic come up a little bit here and there from now on, just to get some reinforcement with it. For now, though, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.